in a company or something similar, you will have to define the exact title in a minute. With that, Chotam, you have the podium. I'm going to record your talk just for the sake of people that cannot attend, with your permission, as you said.
Yeah, no problem. Okay, so hey everybody, thank you for joining me. My name is Chotam Lezerovich. I'm from the Fabrica group of NanoDimension. In the next hour, I'm going to talk with you about a little bit about the company NanoDimension and what the big company is doing. About us, we are the Fabrica group. It's a certain product inside the NanoDimension that gives a solution for manufacturing with single-digit micron precision in 3D printing. So, a few words about myself. I'm in the 3D printing industry since 2014. 5 years in Fabrica Group. I was lucky to join Fabrica right after the idea came to life and to make all the journey with the two founders from the idea till today, until we have been purchased by NanoDimension. I have a BA in economics, and I'm doing MBA with a major in AI and big data. And I came into the 3D printing industry through the open source community. Where with the open source community, I built a 3D printer, and I did several art in the Bern community. And in the right, you can see the printer that we built along the years in the Fabrica group. So NanoDimension, it's quite a big company, not huge, around 400 to 500 people worldwide. NanoDimension have several products. One product, first of all, is our product, right? Okay, it's the Fabrica 3D printer for the micron precision manufacturing. Another product is the AME, is a 3D printer for printing PCB boards. Another product is those two printers, is the 3D printers of Admatec. If you know the company, it's also a company that was recently was bought by NanoDimension. Their major is in printing ceramic slurries and metal. The bottom machine is a pick and place machine by SMTech that have a good integration with the AME, so you can print the PCB and then make do the pick and place of all the components you need. And there is also a GIS company that was bought. GIS company is making an inkjet systems that is a key part in the AME solution. Okay, so Fabrica Group, we are doing a DLP 3D printing. What is DLP? I don't know how many of you know the nuance between the technologies in 3D printing, but so our technology is DLP. DLP means we have a projector that inside the projector we have this DMD chip. Okay, this DMD chips is made out of a lot of really tiny mirrors. When I say tiny, it's around 7 microns for every mirror, 7 on 7 microns. And those mirrors can be like on two states, open or closed. When it's open, the light is going through the mirrors and going to the optics and to the build tray. When it's closed, the light don't go through. So by opening and closing selectively the mirrors, you can make an image and then you can project an image by image by image, layer after layer. And so if you want to make this pyramid, it will be sliced to several images, which will actually look something like this, like the beneath the letter B. Okay, so this is the technology. This is the DLP technology, meaning basically using a projector to project UV images layer after layer to cure the raising we are printing with the material. By the way, if someone have questions along into my talk, feel free to raise your hand and ask the question. Okay, so DLP 3D printing and also SLA have two main ways of printing. One way is bottom up, meaning the platform going all the way down to the glass, and you start printing when you are close to the glass, and layer by layer you are going up, and you are getting far from the glass, but the printed layer will always be close to the glass. And the other method you can do DLP 3D printing is top down, meaning there is no glass. The platform will go inside into the resin tank, and you will always print somewhere over here on the between the air and to the resin. Something you need to understand that oxygen is killing the process of polymerization. So it usually won't be printing on the air. You will have like some kind of foil that will separate the upper resin layer from the air. And for sure, if you want to do a really high resolution printing, if you are doing like a big scale DLP 3D printing, so maybe you cannot use the foil. But anyhow, our method is doing bottom up. Because we like precision, we want to print against a solid structure, which is the quartz glass, that help us to make precision. Our main competitors doing the top-down method. So on the base, we are using a DLP projector that projects UV light on the vat glass, which solidifies the resin. But our innovation is in three main areas. One is the dynamic light systems. We can move the projector and stitch images one to the other. And by that, we have a really high resolution because we're using a pixel size of around 4 micron for printing. But that means that we also, if we are using a 2K projector, it means that the image that we project will be really, really small, okay, around 6 by 9 millimeters. But if we want to make an industrial machine, we need to stitch those images one to another, and by that we are achieving a 50 by 50 millimeters build volume on the XY axis. But keeping the small size pixel size. So this is the dynamic light system we are doing. Basically, it's putting the projector on an XY axis with a really accurate closed loop systems. And the next thing is the smart projection. Okay, so you can't really stitch image one to the other just by putting the images one next to the other with high accuracy. You also need to do it smartly, okay? Because you don't want to make areas that are over-cured or under-cured. because that will impact significantly on the accuracy of small features that are falling on those stitching areas. So we have some smart algorithms that know how to balance those stitching in a good way. And another really important thing is the precision material. Okay, so all the materials we are printing with are homemade materials we developed here in Israel to make a material that will solidify in a 5-micron layer. It's not that simple. Okay, so here you can see this. Those are pictures of our transparent material that is under development. So you can see in the start of the development, we tried to print this cylinder. And you can see that the bottom layers, they went through the previous layer, and the cylinders became to look like a drip. Okay, it's not a cylinder, it's a drip. And here is an example after a lot of developing and balancing all the right materials, and of course the right process, we can make a cylinder that look like a cylinder without an excessive light going through the previous layers that was printed and killing the resolution. So precision materials, it's really important. Smart projection for making the big area, and dynamic light is the key components for succeeding in the micron manufacturing 3D printing. So a little bit of overview on our machine. As I said, we have a projector. This is, by the way, a pretty old version of our machine. Today it looks a little bit different, mostly in the vet area, but that's enough for what we are talking about. So we have a projector on a XY axis on a granite base, that it will be very heavy, very solid, very accurate, with high quality motors that move the X and Y axis. That's how we can achieve the accuracy in stitching. And beneath and above, we have the vat with glass and a foil, fab foil, that we're printing on, and some kind of a stage that's going into the resin and that we are printing on. So we are printing on the tray that is attached to the glass, and leaving for every layer, we are leaving a gap of 5 micron or less. If we want to do 2 micron, then 2 micron, or 10 micron, depends on what is the layer thickness we require in the certain print. But usually we are working with a 5 micron layer thickness. And that's how the printing we are doing the print. Okay, so in terms of materials, so all of those SLA DLP printers use what's called resins, or in the more accurate way, photopolymers, with some additives. The material families are acrylates, epoxies, and vinyl acer. The type of resin we have today, that some of them are already on our customer sites, and some of them will be in the next month or two. It's our black resin. Okay, so this is the resin for daily usage. The clear resin that is somewhat transparent, and the ceramic resin that is ceramic loaded to give the material extra strength. For this certain material was especially developed for injection molding. We will talk a little bit about it along the way. Our materials that we developed can provide a really high resolution for the layer thickness we are printing with and the pixel size we are using, and also the throughput. So just for your ears, so every layer we are printing, every image we are projecting today, we are projecting in 180 milliseconds. That's enough for curing the material to the level we want. If you will look on the market, on the printers that printing today on the market, usually it will be around 2 seconds, 4 seconds, 7 seconds for every layer. So our materials open the possibility of high throughput because we can project for really short terms. And also our materials have loading, like the ceramic loading, and the viscosity we are using today is a pretty low viscosity that will make the process much more easier. So if we are looking on the market, there is a lot of players, not all of them are here, but it's the y-axis is the throughput you can do with your printer and the precision you can achieve with your printer. So here on the bottom there is all the companies of the 2-photon 3D printing, which use another method. They can achieve a precision of nanometers, okay, of like 100 or 300 nanometers of precision, but the throughput is really, really low. And here is us with our main competitors, which are the BMF company. And we are trying to balance between the throughput and the high precision. BMF are more like to print like in the 10 micron layer thickness, and we like to print in 5 micron. Okay, so let's talk about applications. So there is a lot of applications when we talk about micron precision manufacturing. First example is optical lens holders. Okay, so we have today in every smartphone you have a lot of optics, and you need to align those optics very accurately to achieve achieve the quality you want. And today, to make the R&D process of those kinds of aligners, it's a really long process. It can take up to a year, because at first you need to make a mold. And we are talking about a precision mold. So a precision mold, it's something that can take you around 3 months to 6 months only to get the mold and the injection part. And then, and it won't go smoothly on the first try. So you will have another round and maybe a third round to achieve the part you want, the aligner you want for the optics. With our machine, you can print the aligner overnight and look at it and to see if you did all the geometry as you want and you get the expected result. And after you finish the R&D, you can decide if you want to manufacture with the machine or you want to go and manufacture with injection molding. Another application is micro-optical connectors. So also micro-optical connectors are a field that we see it growing is on chips. So today the companies trying to make the chip industry to make all the communication fast as possible, and companies today starting to talk about plug in to the chip with optical connectors instead of wiring. But you need to locate the connector very accurately. So this is also something you can do with our printer because of the freedom of geometry and freedom of making open tunnels, small and open tunnels along the connector, which is something that is pretty hard to achieve with CNC if we are talking about a big aspect ratio. Okay, so to take a drill of 50 micron or 100 micron and to make a hole of 1 centimeter, it's not something that is possible with drilling, but with 3D printing, it's easy. Another application is microfilters. So because of the freedom we get with 3D printing, we can leave the thinking of filtering with holes like we know, and we can start playing with geometry, with lattices, in all sorts of ways to manage to do filtering. This is another example of microfilters. So you can see the 1 millimeter scale, and the holes you see here are around 50 microns. Of course, you can do complex geometries with 3D printing. This is one of the big benefits of 3D printing. You have almost complete freedom in geometry. And then from here, it depends on your mind where you want to take it and what you are investigating. Electrical connectors is also something you can do with 3D printing and with micron precision 3D printing. Again, it's pretty much the same story. Instead of making mold and waiting for the mold to arrive and for all of this manufacturing circle to happen, you can do it overnight in your R&D center. Injection molding. So one of the advantage in micron precision 3D printing for injection molding is that when you inject small parts, the thermal mass is really low. Okay, so there is a lot of companies of 3D printing that tried to print molds for injection molding, but the problem is that photopolymers are not that great with high temperature materials. They tend to break or to fail. So the companies that try to make injection molding with printed molds, they could do 1 shot, 2 shots, 5 shots, but then the mold will break. But when you are going to the micron precision manufacturing, the thermal heat is really, really low because the part is really, really low. And that enables you to make medium-sized batches of like 100 parts, 500 parts injected into the printed mold. So it can help you even after the R&D phase. You can make the short batches, medium batches of manufacturing for the product you are developing. This is an example of a part we printed and injected molded inside. I don't know if you can see, but if you will look on the gear, you can see a writing of a Fabrica. So the thickness of the layers over there, of the letters over there is around, if I remember right, around 20 microns. So you can achieve a really, really high details on your injected parts. And like another nice thing about it, that you can make marks inside your injected part very easily that will define the batch that you are injecting. In contrary, if you would make the mold in CNC, to make on every mold a different mark will be really costly. And with 3D printing, it won't cost you extra money. So once you take the accuracy and you take the material response time and you add on that the ability to stitch images, you can get, when you try to manufacture small parts but accurate, you can make a high throughput that can be a competitor to other industrial solutions. Of course, if you will do big parts that have certain high resolution features, then you won't be as a competitor for industrial solutions, but you can still do an R&D overnight instead of over a month or 3 months. So any questions so far? Because I see I'm getting really quick in the presentation. No? Okay. So a little bit about the process challenges we get when we're trying to do high accuracy 3D printing. So DLP 3D printing, as I explained before, it's basically you go down with a tray, you print on it, then you go up, and then you go down, and then you go up, and then you go down layer by layer by layer. Every time you leave a 5-layer thickness of resin that you solidify by UV light. Now, important thing to understand about it, that after you solidify the layer, you get 2 kinds of forces. One is gluing force to the bottom, and then it depends on what kind of foil you are printing on. And the second force is vacuum. Because you solidified the layer, you create a vacuum between the solidified layer and the foil. The foil and the glass there is beneath the foil. So when you try to go up, which is the retract, you are fighting the vacuum force and the gluing force. The gluing force is almost nothing because we are using the right foil that is anti-stick, but the vacuum force is really, really big. It can vary between 500 grams to 15 kilos. And 15 kilos, it's 15 kilos that your part will feel when you're trying to detach. So it can make a lot of problems, and you need to know how to handle those kinds of forces of retract. What kind of tricks you can do, how you arrange the tray you are printing on, and so on. From the other side, there is the engage force, the force when you go down, okay? So wait a minute. So there is in basically there is the engaged force and retract force, capillary flow effects. There is all around the support structure and material polymerization. Okay, so from the other side there is the engaged force, and the engaged force basically the thinner you go on the layer thickness, the harder it gets, because if you think about it, when you're doing an engage, you need to expel all the liquid resin outside and to leave only a layer thickness of 5 micron or 2 micron. Okay, so if you are doing 100 micron layers, there is no problem. All the fluid will go out. In the area of the viscosity we are living with. Yeah, if you will go higher viscosity, so maybe also 100 micron will be hard. But if once you are going beneath the 100 micron, then the forces are starting to rise up, and I can show you. Do you see the screen, the graph, or the presentation? See the graph? Okay. So this is like a print from today, from this night, and you can see that the engaged forces went up to 45 kilos on the test we did. Okay. So 45 kilos, it's a lot. Think about what it's doing to your machine when she feels 45 kilo of pressure when it's trying to make a single-digit micron precision print. It's tough, but we have ways around. What I showed you here, it's a print that we wanted to make those forces to be really high because we are testing the rigidity of the system. So basically, the thinner you get, the harder it will be, because the forces of the engage procedure will be much more higher, and it can even break the glass in several manners. Okay, another challenge is the capillary flow effect. So we had a lot of customers that wanted to print long and really narrow channels. And what happens afterwards when you finish the printing? All of those channels are filled with liquid, with the resin liquid. And you need to get this liquid out. And you want to make it as automatically, the vision is to make all of the process as automatic as possible, because you want to bring down the hours of human that need to work on manufacturing, not to make it up from the solution you have today in the market. So capillary flow, sometimes we can spend 20 minutes, 30 minutes on a part to clean it from all the liquid that is trapped inside in certain prints. But we are developing automatic ways to handle this situation also, but it's under development, and I believe it will be product that will be released in the next year or two. Another challenge is the support structure. So you need to build a support for your parts, because you can't build the part on the tray, stick to the tray, because the first few layers of printing are not that accurate. The first few layers are layers that are handling the unrigidity of your system, or the high pressure you get in your system. So you're doing some kind of pedestal, and then you start to build support structure, And on the support structure, you have the part. We will see photos in few minutes. But the thing is that you have like this triangle of you want to grip your part as the best as possible, because you don't want any part of your any area of your part to detach and then to be not straight like you want it to be. But you also want to, you don't want scars to be in your part. So if you will grip your part very, very hard, then when you will take out the part, you will leave scars on the surface of your part. So it's some kind of a balance between the scars and the grip you want. And on top of that, you have a stability of your part. So if the support structure will be really thin along the whole build, so when you will do the retract and the engage, procedure, your part will do like this. Okay, it won't be stable, because as long as it will be higher, the support structure will be higher but thin, and then the foundation won't be strong enough to hold your part firmly in the accuracy of the single micron digit. So this is like the triangle that we need to achieve the perfect balance to make our parts with a single digit micron precision. When we talk about material polymerization and depth working window, so we have another triangle. This is the triangle of accuracy, properties, and resolution. So you have the accuracy. So you want to print a feature that is 100 micron. The channel, you want it to be 100 micron. You don't want it to be 105, and you don't want it to be 95. You want it 100 micron. And that requires a certain amount of energy of all the pixels around this tunnel. So you need to decide what is the right amount of energy to get this accuracy, okay? Because let's say if I will project a 4 micron pixel for 1 second, it will be 4 micron. But if I will project it for 2 seconds, so maybe it will be 6 micron. If I will project it for 1 second, but with 1.5x energy, then it will be 6 micron, not 4 micron. So you can play with the gray level, with the energy of the LED, with the time of projection, but you need to take those three and to make them right to the accuracy you want to achieve on this 100 micron tunnel. And by the way, if you want to make, let's say, if you want to make a bump of 50 micron or a bump of 1 millimeter, the amount of energy you will need to use will be different, because the bigger the area that you want to polymerize, the lower the energy you need to use, okay? So this is in terms of accuracy of the tunnel, but also there is a question of resolution. So like we saw on the picture with the drip of developing the transparent material, if I will use too much energy, I will maybe go and penetrate to the previous layer I've printed, and then a circle can be an elliptical. So you need to fine-tune the energy also in terms of resolution. And maybe the fine tuning of the energy for the perfect resolution won't be the energy that will bring you the perfect accuracy. And on top of that, you have the properties of the polymerized material. Okay, so you have some kind of material, and you want to achieve the maximum material properties in tensile strength and so on, or in thermal stability. And maybe the energy for polymerization that will bring you the best properties, maybe it won't bring you the best accuracy. So you have a really delicate triangle that you need to know how to balance perfectly to achieve the maximum from the print process and from your material. And every material requires different balancing. So let's look a little bit of some stuff we printed. So here you can see some kind of filter that the small holes are square holes are 50 microns, 50 by 50 microns. And also, of course, we did also less than 50 microns, but that the pictures I could share with you. But you can see that we didn't clean the part perfectly, and some capillary forces still made the 50 microns blocked. Here is an example of some kind of microfluidic parts that we've been asked to print. Here is the microfilter you saw before, just in the transparent materials. You can see that at first the material was a little bit yellowish, and after further development, it became much more clear on the color. This is another part to get you in the side. So this part was something like my pinky finger in size. Okay, if you will look on the support structure, so those cylinders of the support structures are something like 100 micron, if I'm not mistaken, 100, 150. So this is a really complex part in terms of geometry that we needed to give the right solution of support structure to grip it very good, but also to be able to release it. This is an example of tunnels we've printed for a certain company. So just to understand, every tunnel here is going through here and is connected to a tunnel over here. Okay, so it's not a linear tunnel, it's a round tunnel, and you don't have any way to manufacture this kind of part if not 3D printing. And the tunnel size here is something like 150 microns, that doing like a round shape, which is pretty amazing in my opinion. And you can see also the support structure, how it grips the part where it needs to grip. Here's another example of some kind of fluidic component. So you can see this part was pretty big. I think it was more like of my thumb, a little bit bigger on the sides with the two wings. And you can see there is a thread here. But all of this, also you have a 50 micron hole over here to do something with the fluidics. I don't know what was exactly the application. They didn't share it with us, but a liquid came from here and came out from here from a 50 micron hole, and it went all over this channel. Here is an example of a really tiny part that so this is the part, yeah, and this is like a set of the parts. So this is like, I think, 300 or 200 micron diameter, and because it's really hard to handle by hands, this kind of size, so we took a group of these cylinders and put them inside a set, and then we put them on a support structure. And then after, in the post process, you take all the set, you separate it from the support structure, and then you have the set, and you can take the set under a microscope and start handling the really tiny parts that you wanted to print. This is just a cool support structure that the application engineer, it reminded him of the Mayan pyramids, so he added a nice background. This is, we just printed those deals for Christmas, for the marketing. Came out really beautiful. And here you can see also some kind of a cup that with a really tiny support structures to attach those cups. Just to give you an idea, when we finished the print and finished cleaning the part, we did like this, and it came out from the support structures with a really minimum amount of scars that a regular eye couldn't figure out where the part was gripped. So it was nice. That's it. I hope it was interesting for you guys. We right on time, I think. If there is some questions, so feel free to ask.
Thank you, Chotam. It was actually very interesting, at least to me. I have several questions, but I will let others ask first if there are any questions from the audience. Okay, if there is no question, I will start. You mentioned all these filters early on. The problem that I see is that you cannot really generate in mass, in large quantities. So you mentioned an application for lens holders, for example, that can be used in iPhones and so on, but then you have to be printing in millions. Is that really feasible?
Yeah, so if the applications in the vision going to be millions of parts, so it's less doable. But if you need thousands of parts, then you can.
Okay, but let me ask you the next question then. So how can you generate delicate stuff like this in the millions?
In the millions?
Yeah.
That's a good question, but it depends. Let's say like this. So if the filter is really small and it's not like one filter is 50 by 50 millimeters, but let's say the filters around the several hundred microns in overall size, then you can put in one print around 700 parts.
Yeah.
And then if you have several machines that you will have like 3 shifts a day, so you can make some good amount.
Okay, related question. Okay, maybe somebody else wants to ask anything. Okay, the audience is silent. So I will ask another question. Regarding the support, how do you remove the support if you have any in these tunnels? You talk about problem that you have a capillary problem because of very thin tunnels, but do you have any support inside these tunnels, or no support is actually used there?
No, we don't do supports inside the tunnels.
So, okay, that's something to think about. I mean, what's going on? I mean, what diameter you can or below it, you can give up on support there, because getting support from tunnel is going to be a nightmare.
Yeah, you know, we don't want any support inside the tunnels, and usually tunnel will be usually round. And the beautiful thing about a round tunnel that you can print layer by layer without using support until certain size, because of every layer support the next layer. Yeah.
Sure. But again,
so,
it depends on the size, I guess.
Yeah, it depends on the size. Of course, if you will do like a tunnel of 5 millimeters, so then the last layer you will get some kind of belly. But I can tell you that the part of the tunnel that I showed you, so we send it to a CT to check that everything is open and clear, and it was great.
Okay. Yeah. We have one question from the audience from Ronen Ben Chorin. He asked, what software do you use to create the support? Interesting. Do they have support to simulate the printing to predict the failures and distortions? They mean you.
Yeah, so today we are using a software called Tango, which is a Chinese-based company. There is also a NetFab, and there is Litchi. We find out that Tango are the best compromise in the market from our side, but still there is a lot of problems in generating the support with them, and we hope for a better solution in the future. And what was the second part of the question?
That was the question. And do you use any software to simulate and predict failures or distortions in the result?
No.
No, okay.
We don't have simulation.
Okay, any other question?
Robert Davis here want to ask something.
Okay, please.
Yes, can you hear me? I'm not
yes,
sure.
Yes, we can.
Okay. I just wanted to know the materials you're using. I don't know, I didn't hear what are the thermal or the mechanical limitations on the materials? It seems like they're prototypes, but I don't know if they can be used in very stressed conditions.
Yeah, so it depends on what is the definition of stress conditions, but so today we have one strong material that is the ceramic loaded material. All the data sheets should be on the site, on our site, on the website. I can tell you that they can reach today for around 100, if I'm not mistaken. Don't take me for 100% granted, but it's around 160 degrees. But I don't remember like tensile stress and stuff like this.
They Celsius or Fahrenheit?
Celsius.
You have to be
but this kind of info should be in our website, and if you can't find it there, so feel free to send us a mail about it.
Yeah, you can send me email and I will forward it to Chotam, no problem.
Sure. Okay.
Okay, any other question? I have a minor question, maybe the last one. I mean, you mentioned that you have 5 microns between layers. What's the XY accuracy? I might have missed it.
So the XY accuracy is 300 nanometers.
Okay.
Because once you want to stitch like a 5 micron pixel one to another accurately, you want to be less than 1 micron accurately in XY.
Okay, fair enough. Okay, thank you very much, Chotam. Thank you, everybody. It was very nice talk, and the talk indeed will going to be on the web in the next few days.
Thank you very much.
And see you next month.
Thank you.
Bye-bye.